Hey, lesson 102 is called Growth and Decay. We've talked about sequences where the ratio between two elements in the sequence is constant. For example, in 1, 2, 4, 8, and so on, it's always times 2. So the ratio is always 2. If you take a number over the number that came prior, so if you take 2 and you put it over 1, and you make that ratio, it's 2. You pick that for any two consecutive numbers, right? You put 32 over the number it comes after. That constant ratio comes to 2. It's really, you can think of it as a multiplier, right? We multiply by 2 every time. Okay? If it's becoming smaller, then your multiplier is a fraction. If the number is dropping in half, then your multiplier is half. The ratio, you take the number over the number that came before it, and you'll realize it's getting smaller. That's called decay. The first one was called growth. Makes sense. We've got a couple examples in everyday life. You'll find this a lot in the financial world. We'll talk about something called the Rule of 72 just briefly today. But let's talk example 1. For growth, the population of a county grows 2% per year for 5 years. If it's now 1,200,000, what will the population be in 3 years? So it starts at 1.2 million. How do we find out at a 2% growth rate what it would be in 3 years? There's no shortcut, really. You take 1.2 million. Now, what would be 2% more than that? How would we find that? What's its multiplier? The multiplier would be 1.2. 2% more would be 100%, 1, plus an extra 2, because we want 102% of what we started with, right? So the multiplier, we divide by 100, you use the divided by 100 version of that. Let me pull up my calculator to find what that would come to. $1,040,000. That was after how many? 1 year, right? Okay. Now after 2 years, we have to multiply. Same thing. Okay. That's how you have to do it so that your end up being correct. But now you've already got it in your calculator, so it doesn't take as much work. Let's just skip ahead to one more. In the third year, it would be 2,073,000, and I think it said 600 after 3 years. Did something wrong, didn't we? 1.02. I even wrote that correct right here, didn't I? And then I wrote it wrong down here. So if we make the fix, and we do times 1.02, now you know how that can go wrong sometimes. Let's do that 3 times. Some of you may have caught that while I was doing it. 1,273,449. So they rounded to 450. What was I finding? I was finding 20% per year. That's why I doubled by 3 years. Now it also asks, using the rule of 72, about how many years will it take for the county's population to double at this rate? Okay, the rule of 72 is used the following way. You divide 72 by the percentage that we learned it's growing, which is 2%. When you do that, it will tell you how long it will take for it to double. So you take 72, which is just a magic number they found works. You divide it by the growth rate, which is 2. And the answer, 36, is how many years it takes for it to double. That's just the magic of that number. Keep example 1 in mind on how to use the rule of 72 if it ever comes back. We don't talk about it a lot, but it is in the financial world a lot. So I've encountered it in everyday life. Speaking of things I've encountered outside of math class, carbon-14 dating, we have mixed feelings as Christians because of some of the conclusions that are reached using it. It's a flawed dating use. Assumptions are flawed in the use of carbon dating, but for the sake of math here today, let's use carbon-14 as a radioactive isotope occurring in nature. It's used to date materials that have carbon in them, such as once living plants and animals. It has a half-life of 5,730 years, meaning it takes 5,730 years for half of its carbon to disappear. So they try to use this to date really old things. If a bone is found containing about a fourth of the amount of carbon-14 as a modern-day one, how old would you say it is? We would find this by, so if a fourth of it's there, that means it lost a half and then another half, right? Because that's what a fourth is. So it's had 2 half-lives. A half-life is worth 5,730 years, it said. So we're going to do that twice. That's going to come out to about how old? 11,000. If you're a little bit unsure, they're all pretty far apart answers, right? This is one where it actually hasn't even reached a full half-life yet. This is just 1 half-life. This is 2 half-lives. So we figured, well, if it loses half every 5,000 some years, then it'll take 2 of those lives to reach a fourth, because it's a half and then times a half. You can read more about that in example 3 if you'd like. And then why don't you try A, B, C, and C again, which should say D, because all 4 are different and all 4 remind me of the different things we learned today. All right, do your best.